So I'll start, I'll try to be gentle and start with some very basic definitions, very basic notions. So assume that we have some probability space with the filtration, and let J with the sigma field J, calligraphic J, be a measurable space. We call it a jump space. So a jump space is a space where our random measure basically lives. So mu from the sigma algebra Brownian, Borel on R plus times the J calligraphic times omega to R plus is called integer valued option random measure. If it's almost surely a measure on this product space, if it takes values in integers, and if it's adapted. So for any A and J, the measure of mu 0t times A, this can be infinite, but it's still a process which can take values in plus infinity. This process must be adapted. So within the talk, I often will skip this integer valued optional, but just tell random measure. A random measure, now it's not necessarily integer valued. It's called predictable if, well, we have the same property, but our random processes for the integrals, for the measure of 0t times A are actually predictable. So a classical example of a random measure is, of course, a jump measure. So if you have a Cadillac adapted process F, with values in some Banach space X, then you can define J as the jump space to be X itself with the corresponding Borel sigma field. And you can define the following random measure mu F as the measure collecting all jumps of F within the set A, where A is, I'm sorry, it's not, yeah, where A is in J, so it's a subset of X. So it just collects all the non-zero jumps, of course. So, so this is a standard random measure taken in mind. And of course, if your F happens to be not adapted but predictable, then you would have a predictable random measure. It's fairly simple to integrate with respect to random measures because if you have random measure, it's something positive. You can integrate any positive function with respect to random measure, get something maybe infinite, but it's still kind of, the integral is well defined within the range of R plus bar, so R plus and plus infinity. So you can define for any predictable, or actually for any process, you can define a stochastic integral with respect to a random measure mu. So we call it G star mu. And then what comes next is that if a random measure is good enough, so what means good enough? It means that it's sigma finite with respect to the predictable sigma field. So a good enough measure always has a compensator, so a unique predictable random measure, which must not be integer valued, nu, such that for any G, which is integrable with respect to mu in such a sense, so expectation of G star mu infinity is finite. One has that it's also integrable with respect to this measure nu, and those integrals coincide. In practice, this actually means this is equivalent to the fact that G star mu t minus G star nu t. So this process is a martingale. So that's why this measure is called the compensator measure. We compensate our integral with the compensator in order to make this integral a martingale in time. So yeah, so within this talk, until the very end, I will be talking about a very specific case of random measures when you have a deterministic compensator. So we will assume that our nu is deterministic, and in this case, if nu is deterministic, mu is actually Poisson. What does it mean? It means that mu of 0t times A has a Poisson distribution with parameter nu of 0t times A. A classical example in the real life could be like drops of water or chew gums nearby the train station. So nu corresponds to some intensity. This intensity of chew gums is closer to the entrance of the station and smaller outside of the entrance of the station, but it still gives you only the chance that the chew gum will appear there, right? but with which intensity you would have a chewgum within this particular square meter of your train station. So yeah, and in this case, of course, all these processes, all these random variables are independent, given you have independent domains. So we're interested in the question of stochastic integration. And we will simplify it even further. We will assume that our random measure has a compensator which is not only deterministic, but it's a Lebesgue measure in time and some measure in jump space, some new node in jump space. So we're actually in the situation when you have compensator which is the same in time, homogeneous in time, basically, right? If you shift it, it doesn't change. So we will be working with stochastic integrals of the so-called symmetric integrants because we want our integral to have symmetric distribution. So G is called symmetric if for any A from B of X, well, if we talk, for example, about, I'm sorry, yeah, if for any A from B of X, for X valued G, one has that nu naught of G in A equals nu naught of G not in minus A. It is in minus A. So here must be, of course, GT. I'm sorry. Here must be GT for all times. So that our integrals provide the symmetric random variable. So the first classical result in this direction was by Novikov in 75, which has shown that LP moments of the integral can be bounded from above by either minimum or maximum of LP or iterated LP L2 norms with respect to the compensator nu. So before going to the story on Banach spaces, I want to first provide a very simple elementary result, how this can be extended in some sense to Banach spaces. And Banach space X, let X be Banach space and P be between 1 and 2, then X has type P if for any Xn in X and for any independent Rademacher, one has such an LP bound. So LP bound for a random sum, a Rademacher sum of An Xn to the power P is bounded by the pth moment of the sequence of Xn's. So this is a typical standard definition. Like every Banach space has type 1, it's just by triangle inequality. If it has some type bigger than 1, then it has all types within 1 and P. LQ always has type between 1 and minimum 2 in Q. And in particular, every Hilbert space is isomorphic to L2, so asymmetric to L2, so every Hilbert space has type 2. So then we can actually kind of extend, it's not a per se extension of the theory of Novikov, but it's kind of, it's extension for pth smaller than 2 in a sense. So let X be a Banach space. Then it has type P if and only if for any random measure with such a compensator and for any symmetric G, one has that the pth moment of the stochastic integral of G with respect to mu is bounded by the pth moment of G with respect to nu. So this is the statement. So it's very close to the Novikov statement here, because here we have also the same pth, but it also provides us with this estimate because we can prove something for p equals 2 and then use the so-called Lenglad inequality. It somehow allows us to prove inequalities for LPs for p smaller than 2, for example, in this case. So yes. So it provides just one estimate, which is rather elementary, but one can, of course, go further. I will not go through now through all results on strong LP estimates in Banach space setting, but I only want to mention that in this case, when you have such type of upper estimates, you can actually also show a lower estimate. So I will just show you how it works with Novikov inequalities. So if you have some upper estimates with some norm depending on your compensator and P, then you can use the so-called duality argument, sometimes, not always. So what does it tell? If you have this, well, integral operator, say T, is bounded from X to Y, in the case X being, for example, some LQ-valued processes, and here will be something like, also LQ-valued random variables, right? But the same, you know that the same operator is bounded from X star to Y star. And you know that the inner product of Tx star equals the inner product of X star. Then what you can actually do sometimes, if, for example, you know that the image of your operator T is dense in Y or norming in Y and in Y star, you can show that if you have here, well, because it's a bounded operator, you have upper bounds, you actually can prove also lower bounds. So instead of having upper bound, you may have actually lower bound. So instead, in Novikov's, by applying this duality argument, you can show that that you would have actually equivalence. And here you see some strange norms, but those norms are nothing but intersections of spaces and sum of spaces. So in this case, for example, you have Y, which corresponds to the intersection of LP of integrated LP plus, intersected LP of L2. And here you have Y star, the intersection, the star to the intersection space would be the so-called plus space. So plus LP prime of L2. So in this plus space, it's non-defined here. It's a maximum of all decompositions of G into G1 and G2, where G1 lies in one space and G2 in the other space. So in fact, you can actually show two-sided estimates for real values, and you can actually also show it for Hilbert space values, like if you use upper bounds from Marinelli and Rockner. And I guess the most well-known result in this direction was done by Schuer-Dixon, where he has shown upper and lower bounds, like sharp upper and lower bounds, for LQ-valued processes with actually 6 cases. So like you have P, Q, and 2, and with different rotations between P, Qs, and 2, you can find the corresponding triple norm, which kind of will have different forms. So this is about the strong inequalities. You can show a very, very simple one for type P, and you can show actually much stronger and much more maybe beautiful in some particular cases. So now let us move to weak type estimates. So for weak type estimates, we'll need something which are called alpha stable random variables, which turned out to be very important in this setting. So let alpha be between 0 and 2. We exclude 2. A random variable xi is called a symmetric alpha stable if its Fourier transform is e to the power minus c absolute value of lambda to the power alpha for some constant c. So they depend rescaling-wise. So and corresponding the Levy process, a Levy process is called symmetric alpha stable if it has symmetric alpha stable distribution. So alpha stable processes are super standard in the sense that they rescaling-wise, they coincide with each other, and this is kind of an important property. So they are like Brownian motion, but more, but having jumps, basically, right? So yeah, some example, if you send alpha to 2, of course, you get Brownian motion. As L has pth moment, if and only if P is strictly smaller than alpha. L has weak pth moment, if and only if P is smaller or equal than alpha. And L has bounded variation if and only if alpha is smaller than 1. Then we have the following real-valued results. Now it's about not random measures, but alpha-stable processes, which tells us that weak L alpha norm of an integral with respect to an alpha stable process is equivalent to the integral of alpha of absolute value fs to the power alpha ds. Expectation of it, because, well, okay, it's, I wrote here elementary, but it can be also predictable. It can be also predictable. That's why one can put expectation here. So this result due to Gine, Markus in 83 and Rosinski, Wojcinski in 86. So yeah, actually you see here that we have only alpha stables, but not a general random measure, but you have equivalence. So the thing is that one can actually extend this result to Banach spaces and to general random measures. So how do we extend it? First, we define the so-called stable type alpha stable type alpha space. Let X be a Banach space and alpha be between 0 and 2. Then X has stable type alpha if for every p smaller than alpha, or for some p smaller than alpha, for every sequence x n's, and for any psi n symmetric alpha stable independent random variables, one has that the pth moment of a random sum is bounded by the alpha moment of the sum of x n's. So here we cannot take p equals infinity, because recall, stable type alpha stable random variables do not have moment alpha. They have only weak moment alpha, but we can go below, we can take p below alpha. So this is a very boring definition, I know, but it has a nice equivalent definition, which I'll show in a moment. So first, every Banach space has stable type alpha smaller than 1. If you have stable type alpha, then you have any stable type below. And it's, I guess, more important, if you have type alpha, then you have stable type alpha p strictly smaller than alpha. So what happens is that if you have a Banach space X, and this is your closed interval between 1 and p where you can take your type, so you have maximal type p, here is 0. So the thing is that, so it's type p is like a maximum type you can take. A stable type is the same, but you just literally exclude one point p. So if you have stable type alpha, then you have stable type alpha plus epsilon for some epsilon. If you have type p, then you have a stable type alpha for alpha smaller than p. Okay, so this is actually can be used as a definition. X has stable type alpha if it has type p for p. For p strictly for p. I'm sorry. It has stable type alpha. If you have stable type p for p a bit bigger than alpha. Okay, so you only exclude 1 point. Yeah, and also some properties that LQ has stable type up to minimum Q, 2 and Q, like with types, and every Hilbert space has type smaller than 2. So this is a very specific. Those are very specific Banach spaces, but well, okay, you can use some LQs or some interpolation arguments for maybe Lorentz spaces, etc. And so the major result is as follows. Let alpha be between 0 and 2, and X be a Banach space, then X has stable type alpha, if and only if, for any random measure mu with a compensating u, and for any elementary symmetric G, the weak alpha norm of integral of G with respect to mu is bounded by integral over time of weak norm of G itself with respect to this measure nu naught dt. So this is the major result. And the proof is based on Rosinski's paper, where for the stable type alpha, you can have such type of inequality for x-valued random variables, independent symmetric random variables psi n's. So sum over n psi n. Weak norm is bounded by sum of weak norms. And as a corollary, you can extend then the definition of your stochastic integral to all g's satisfying these conditions. So it's like a typical thing you do in this theory. You go to Banach space valued integrals and you prove something for elementary processes and then extend it to all processes. Yes, so what happens if we take now stable type alpha process as an integrator? So let D be a dimension. So Xi is called symmetric alpha stable D-dimensional if it has certain rescaling properties. So if you consider A1 Xi1 plus A2 Xi2, then it would have the same distribution as A1 to the power alpha plus A2 to the power alpha to the power 1 of alpha Xi for any A1, A2 bigger than 0, Xi1, Xi2 independent copies of Xi. It's called an alpha stable random variable, and then you can define an alpha stable process in D dimensions as a Levy process, symmetric process with alpha stable distribution, right? So, and then we can actually have a full analog of the one-dimensional result. So let alpha be between 0 and 2, and X be a Banach space, then X has stable type alpha, if and only if one has such a equivalence of weak L alpha norms for integrals with respect to a symmetric Levy process. Here what appears is a very strange guy, L nu naught of GS to the power alpha, but it's nothing but, okay, it's some tail type estimate on G as an operator. Yeah, now G is an operator valued because our L has values in RD, so G must send RD to X. So it's operator valued, and we want this operator to have certain, it's not a norm, but it's kind of certain quantity, which I guess for alpha bigger than 1 should be kind of norm. Yes, should be norming, I guess. So, and the proof of this equivalence can be shown via well, I mean, the important part here, of course, is to just read one book by Linde on alpha stable distributions. So, yeah, the proof follows basically certain properties of alpha stable distributions in this case. And yes, and it's a bit similar to the results on Brownian motion by Van Neven, Ferrar, and Weiss, because recall that in that result, one was considering recall that in that result, one was considering integration with respect to Brownian motion in Banach spaces, and then telling that this is, in the case of deterministic function, this is a Gaussian random variable itself. So there are no estimates. You just estimate kind of the Gaussian random variable by its, I don't know, its second moments. So here it's kind of the same, because when you integrate here G with respect to a alpha stable process, you get again an alpha stable random variable. So integral of G dl, it's an alpha stable random variable. And so you need to bound it from above and from below. You need to bound its weak L alpha norm, which happens to be quite a good thing because of the properties of alpha stable of Banach spaces with stable type alpha. Yes, and recall, yes, that for example in the theory of a Brownian motion, what one has is that okay, if you assume something like type P, you would have something like an upper bound, so something like an upper bound integral over R plus, and here would be some integral of some norm of phi, in a sense, dt. Oops. But here you have actually equivalence. So it's for some reason, I guess, somehow here is some misunderstanding between the theories, because for type P, you have only upper bounds, but for stable type alpha, for some reason, you have equivalence. So you can characterize the integrants. Yeah, and what worth noticing is that this L new node, this new node, it's actually it's related to our L, and it actually comes from the Levy measure in Levy-Khinchin formula for our alpha stable process. So this is where we gain our information. So a couple of words about extensions. So the first one is that instead of considering here just d-dimensional process, one can consider bounding space valued process, or even more general cylindrical alpha stable processes, and you would still get a characterization result for stochastic integral. It still will be possible. And then, well, what one can do throughout the talk, we assume that G is deterministic, but of course, we can go to predictable Gs. So, so G deterministic, but you can go to predictable Gs with some costs, but with some cost that you cannot that you need to assume something about your Banach space in order to have your weak L alpha norms or semi-norms to be comparable. The cost is that X must be UMD minus. So UMD minus means, well, okay, any Banach space should fulfill this. Okay, so not every reflexive Banach space is UMD, but if you come up with some example of a reflexive Banach space, highly likely it has UMD property. So this is your cost you pay in order to have here any predictable G. You can go further. Our measure mu had a deterministic compensator. You can make it also random, which seems to be standard because sometimes in some processes, like for example with these two gums, either there are no gums or somebody threw out a gum, and then people started realizing, oh, we can throw a gum and also put a lot of gums there. So somehow your compensator may depend on the solution of your SPD. And in this case, you want to make your compensator random, so you can make your compensator deterministic, so you can make it random. And it's also kind of with the same cost of UMD. And in this case, you would use something like, instead of measure mu, which you would use the so-called Cox process. So it's with this cost of UMD space of X being UMD, you would have weak L alpha bounds for integrals with respect to the mu and with respect to the Cox process, which is a process which has conditionally independent increments somehow, if to say so, this random measure. So it's kind of has conditionally deterministic compensator. So, and this is what we then use. And of course, throughout the talk we're talking about symmetric integrants, but you can make them asymmetric for alpha bigger than 1 just by using conditional expectation. And the further questions which may be interesting in this direction is whether there are lower bounds. So like here we have equivalence, but one would like to have equivalence also here for general random measure, whether there are some lower bounds. To be honest, the chances are low, just because lower bounds, they heavily depend on these alpha stable processes. For some reason, alpha stable processes or alpha stable distributions are the only kind of, or not the only, but the most well-known candidates for this inequality of Rosinski to be actually equivalent. So if you plug in here alpha stable distributions, then you would have here an equivalence, and that's why actually you have here equivalence. So and that's why there are no no hope for lower bounds, and therefore maybe the lower bounds can be obtained not for general random measures, but just for some of them, for some specific distributions. So I guess that's it for now. Thank you so much, and let's get questions, please ask.